All right, we are back with episode number 23 of the Piezo SHOCK Show. And we're going to answer a really good question here. And this is kind of the start of a series of answers, specifically with regards to how to design a bolt Langevin transducer. So that is, what is the significance of wavelength? We always hear about wavelength when we're discussing ultrasonic transducers, namely the ones I speak about in this show are resonators. And what's the importance of that wavelength for the design of ultrasonic transducers? So today I'm going to describe what is a wavelength. We're specifically talking about the wavelength of sound. In this specific video, I'm going to be only speaking about longitudinal acoustic waves or bulk acoustic waves that kind of travel through the bulk of the medium. They're not bending. They're also considered longitudinal or axial waves, which is what like welders or ultrasonic cleaners or most devices actually take advantage of for their primary mode of operation. So what is the wavelength? So here we go. So we have the speed of sound of a material, and the rate at which these acoustic waves travel in the bulk of the material, which is related to the square root of the density divided by the elastic stiffness in that dimension. So there's very you can find equations for that and values for that for a variety of materials. Steel, as we're going to be discussing in the next two slides here, is 3,000 meters per second to give you a relative estimate. For example, water is going to be lower than that. Air is because it's not dense at all, and it's also very not stiff. It's going to have an even lower speed of sound. So just to give you an idea of how all that works. Next equals frequency. The units of frequency is 1 over seconds multiplied by wavelength, whose units are meters. So you can understand meters per second, wavelengths per second, or wavelength times frequency. So solving this equation for wavelength, basically dividing speed of sound by the frequency at which the sound is introduced or exists in the material or the sample that you're talking about, that's going to tell you the wavelengths, basically the distances between the maximum points of oscillation in the same direction, or the maximum points of strain or stress. So we have this equation, the speed of sound, which we'll write V, equals the frequency multiplied by the wavelength. So let's say we have this long steel rod, and we are applying a hammer. We're applying some type of impact force at 10 times per second. What is the wavelength in between those traveling waves that are going through the material? We're not talking about resonance here and the reflection that's going to come out on the other side of this rod. We're just talking about, in this case, just going one direction. So if you use this equation, the speed of sound divided by the frequency, which is 10 times per second, we use the speed of sound value of 3,000 meters per second, which is approximately that of steel. We're going to come up with 300 meters in between this, in between each one of these impulses within the material. So if you're like measuring the impulses, it's going to be, or if you had two sensors showing the distances in between these impulses as they kind of propagate down the rod, it's going to have traveled 300 meters. Once you hit it one time, the next time you hit it again, this is 10 times per second, which is not humanly possible, but it's possible with other mechanical structures, electronics impulse there. So by the time you hit the next one, and that every 10 seconds, every 100 milliseconds, basically, it's going to have traveled 300 meters down. So that's quite a long distance. So what about here? And the difference between this slide is here. What if we do this at 30,000 times per second? Now, normally, in order to do that, get that frequency of impulse, well, you need a piezo crystal that can easily handle that rate of oscillation. You just have to put a sine wave of 30 kilohertz, and you therefore have a 30 kilohertz sound generation, acoustic generation source. So let's say it's 30 kilohertz. Now, if you do this whole equation using the same speed of sound, you're going to end up with 0.1 meters. That's about 4 inches. And between these impulses. So now we kind of figured out and got an idea of speed of sound and the distances in between these impulses and how do you calculate wavelength. So let's go to the next part. See, this is this is a wavelength here. From, if you see the stress is increasing here, and there's a stress maximum, and then you have another stress minimum. So the stress minimums are also going to correlate and be exactly the displacement maximum points. So if you find one wave, from top, not from here to top and back down, we have to come around again, and as a sine wave, you have to perfectly replicate this shape in order to be considered one wavelength. So here's where we get to the actual practical significance of wavelength. So we have a rod here, and a rod, if you just have it kind of free floating, it's going to have free boundary conditions, and those free boundary conditions are zero strain conditions on the bar. What this basically says that any excitation that occurs, the resonant frequency that it's going to stimulate are going to have basically zero stress, or which is also maximum displacement conditions on the edges. So the permissible sort of number of modes is infinite, but the lower order modes, which are going to be excited with the most strength, start with the half wavelength. And the half wavelength is the first sort of mode shape, as we call it, that supports maximum. This is displacement. All these plots are displacement. It supports maximum displacement on the edges. Now we see negative displacement here and positive displacement on this side. This just means it's expanding. The two edges are moving away from each other, causing kind of a net strain, a net stress in the material. It's the stress, if you were to draw it here, it's always going to be, so this is increasing. So the net stress is going to be maximum in the center and also minimum at the edges, or zero actually. And then the increasing wavelengths come here. So this is 3 pi over 2, this should be 3, and this should be 5 pi over 2. So basically, as we keep increasing in the mode number, we also have different number of wavelengths in the material. These will also be higher frequencies, right, according to these ratios as well. So these ratios and wavelengths, depending on the frequency you apply, you will excite certain wavelengths within the material. So it's important then to know your wavelength, then to describe what frequency, where your nodes are going to be, where you want to put your piezos and attach your other components. All right. Let's go to the next slide here. So here we have a clamped free condition. And in the clamped free condition, which is very similar to what case, where you have, let's say you have a transducer, and then you have a stepped horn, right? You have a stepped horn, some type of, whether it has curvature going down to the step, or whether it simply just is this kind of an abrupt change, that actually closely looks similar to this case, where you do have you could say a heavy mass, or a clamped light condition. So this is very similar for a stepped horn, or a smooth transitioning horn, where the wavelength is now clamped on one side and free on the other side. The mode of oscillation, or the mode shape, which is excited in this case, is a quarter wavelength. So the quarter wavelength is also pretty important for your design of your transducer, especially for horn design. Utilizing and understanding these wavelengths, putting your nodes specifically at the piezos, and also your antinodes, which is the maximum displacement points. Both, obviously, they're going to be at the edge, but also at those component interfaces in the transducer is going to be important. And I'll describe that a little more. So if we go to the next wavelength, it's going to be 3 wavelengths over 4, and that's going to be the next permissible mode in this case. So how does all of this apply to designing a transducer? The first thing is, this applies because we have nodes at our piezos, and that's how we do our design. The piezoelectric materials, they effectively generate stress and strain, and therefore we have to place them at nodal points. We don't place them at the antinodes where they have the maximum displacement. They actually generate stress and strain. It's a better, more accurate way of looking at the operation of a piezo. So it helps us to design our transducer such that that's where we put our piezos, or close to that, and maybe may differ, but for all purposes of this discussion, we put our piezos at or close to the nodal points. The next is when you assemble multiple components together, like in many cases you have a transducer, and then you screw on and you attach other tools, other horns to that mechanism. And the wavelength of those tools needs to match, let's say, the wavelength that you optimize your transducer for. So your transducer still operates in the same mode shape, like it has a maximum displacement at the same point, it has the node points right where you designed it for your piezo. They all kind of work together in the same way, even though you just attach this big tool. It could be very long, but if you have the wavelengths of your tool appropriately matched to your transducer, then the frequency will remain the same, and you will still have efficient drive of that tool, despite it being very long. Because in some cases, I know for many ultrasonic surgical tools and also for welding transducers, there's many attachments done to the base transducer, and they can get over 2 to 3 times longer by attaching these tools. However, designing that tool according to your transducer will then, according to the frequency of the transducer, will then allow you to maintain your optimum form of the mode shape in operation. So again, when you're attaching the tool, you want the tool to be at the attachment point is going to be at an antinode, at a point of maximum displacement, in order to minimize stresses at interfaces. Stresses at interfaces are a really bad thing for ultrasonics. It's much better for it to be a high displacement point. That works much better for transferring energy rather than having it to be a stress concentration point. So basically, you can stack components if you know that the wavelengths. Also, we want to put interfaces, I mentioned, at antinodes. So the first one was put the nodes of the piezo. The second was we can stack components together. We'll know that how we can conserve our resonant frequency and thus optimize our transducer. And then you'll have different tools of different lengths to be able to understand how long we need to make it and which tool will fit where. So also interfaces should be at antinodes in order to maximize the power transfer and allow you to operate in higher power operation. Otherwise, you'll have a stress concentration at your component interfaces that's going to lead to nonlinearity, loosening of that tool, and other unideal behaviors and characteristics. In FEA, this won't matter at all because you have perfect kind of bonding in between components. But this is like one of the differences between FEA and reality, whereas this won't matter as much to have an antinode at your interface, at your interfaces, but in real life, you're going to experience that difference immediately. So that's this one thing to keep in mind, a rule of thumb that you get from experiments that you won't get from an FEA simulation, or the effects of it won't show up. So I have those interfaces at antinodes, and just kind of as a recap here, pi over 4, that's the factor that goes from a node to an antinode. So assuming you chose your frequency, then you'll have your wavelengths. And then you'll be able to obviously calculate your wavelengths from frequency and speed of sound of the material, which are more or less known for whatever material you're going to work with, including PZT. And then also, a half wavelength is going between antinode to antinode. And that's the other important component. If you want to have a transducer, and then you want to have a component attaching to it like a horn or something, which something else will come onto it. So you have your transducer, you have some type of a horn structure that let's say it's replaceable and removable. Then you want to have another structure at the end, let's say that's a tool. So you may want to have your transducer work at a half wavelength such that the nodal point is in the middle. Then you want your horn to be, let's say you want that also, let's say, to be a half wavelength. So then you can interface, or it won't be a horn per se, because that has a little bit different. Let's say this is a coupler, so you have that coupling component in between, and that allows you to go from half wavelength to half wavelength. So now you kind of have a full wavelength happening. And then you can have your transducer, and let's say it's a horn with the tool at the end, and that could be a quarter wavelength, for example. So you can kind of rack up these components and conserve frequency, and also give yourself a little bit easier time in design, because it's very confusing if every single component you add on changes frequency and characteristics. That's just gets to be confusing. This method of calculating frequencies and establishing standard lengths of tools and frequency operating conditions is a pretty common practice. But yeah, I just wanted to make this episode to elucidate that. You've been watching episode number 23 of the Shock Show. I hope you enjoyed it. Please leave comments and questions. I look forward to getting back to those, as well as check out some of the links in the description that'll allow you to sign up for updates, receive some of these presentation notes in your email, and also there'll be a link to check out my consulting services for ultrasonic transducer development and analysis. Thank you for watching the Shock Show, and I'll see you tomorrow in episode number 24.